Hey everyone, welcome to Instrumentation Lectures. We had started our discussion on static characteristics in the last video and we covered the parameters like span, range, accuracy and precision. So, if you need to refresh these topics, please watch the previous lecture. In this video, we are going to study about all the remaining static characteristics. So, let's start our lecture. The first parameter we will study is static error. It is defined as the algebraic difference between the value indicated by the output of the measuring system and the true value of the quantity presented to the input. To put it simply, static error is equal to measured value minus true value. So, if the measured value is greater than the true value, then error is a positive quantity, and otherwise error is a negative quantity. This way of expressing error is also called absolute static error. Now, this absolute static error has a drawback. It does not precisely indicate the accuracy of measurements. As an example, say you are measuring a current of the order of 1000 ampere and the error in measurement is plus or minus 2 ampere. The error of plus or minus 2 ampere is negligible in this case. However, the same error of plus or minus 2 ampere may be regarded as intolerable when the current under measurement is of the order of 10 ampere or so. So, in this case, the error is tolerable. However, when the current is of the order of 10 ampere, the error of plus or minus 2 ampere is intolerable. So, we can say that simply absolute static error does not give us any idea about the precision of instrument. Therefore, to get the quality of measurement, we define another term, relative static error. Relative static error is the ratio of absolute static error to the true value of quantity under measurement. That is, relative static error ER is equal to dou A by AT, where dou A is equal to AM minus AT and AM is equal to measured value of quantity A, measured value of quantity A, and AT is true value of quantity A. Sometimes relative static error is expressed in percentage as percentage ER is equal to ER into 100, which is dou A by AT into 100. Now we know dou A is equal to AM minus AT. So from here we can write AT is equal to AM minus dou A. And using this relation we get dou A is equal to ER into AT. Therefore, AT is equal to AM minus ER into AT, or AT into 1 plus ER is equal to AM, or AT is equal to AM by 1 plus ER. Just keep this relation in mind, okay? It will be useful for you. Also, when the value of dou A is very small, the value of ER becomes very much less than 1, and as a result, this equation becomes AT is equal to AM into 1 minus ER. Okay, just keep this in mind. So, we have covered static error, and the next parameter we need to learn is correction. Static correction is the difference between the true value and the measured value of the quantity. That is, static correction dou C is equal to AT minus AM, or is equal to negative of dou A, that is static error, where AT is the true value of the quantity A and AM is the measured value of quantity A, and as defined, dou A is equal to AM minus AT. Let us now see an example on static error and static correction. A meter reads 127.50 volt and the true value of the voltage is 127.43 volt. Determine static error and static correction for this measurement. So first let us write down the given values. Okay, here the meter reads 127.50 volts. Therefore, measured value AM is equal to 127.5 volt. And the true value of voltage is given as 127.43 volt. Therefore, true value AT is equal to 127.43 volts. And we have defined static error dou A as AM minus AT. Therefore, 127.5 minus 127.43, which is 0.07 volts. This is the static error. Also, we learned that static correction dou C is equal to negative of static error, which is equal to minus of 0.07 volts, which is minus 0.07 volts. So this is static correction. Let us see one more example. Okay, a thermometer reads 95.45 degrees Celsius. Therefore, the measured value AM is equal to 95.45 degrees Celsius. The static correction given in the correction curve is minus 0.08 degrees Celsius. Therefore, static correction dou C is equal to minus 0.08 degrees Celsius, and determine the true value of the temperature. We know the relation dou C is equal to A true value minus A measured value, which gives us A true value is equal to dou C plus AM, which is minus 0.08 degrees Celsius plus 95.45 degrees Celsius, which is equal to 95.37 degrees Celsius. Okay, so this is the true value of temperature. Now another question is, a voltage has a true value of 1.5 volt. Okay, so AT is equal to 1.5 volt. Also given, an analog indicating instrument with a scale range of 0 to 2.5 volt shows a voltage of 1.46 volt. So the measured value given is 1.46 volts, and also the range of the instrument is given as 0 to 2.5 volts. Okay. Now the question is, what are the values of absolute error and correction? We know that absolute error dou A is equal to A measured value minus a true value, which is 1.46 volt minus 1.5 volt, which is minus 0.04 volts. And we have static correction dou C is equal to minus of dou A, which will be minus of minus 0.04, which is plus 0.04 volts. Now the next part of question is, express the error as a fraction of true value and the full scale deflection. So we are asked to find the relative error. Relative error is equal to ER, which is dou A by AT, which is minus 0.04 by true value, which is 1.5 volt, which is minus 0.0266, or this can be expressed as a percentage as percentage ER is equal to minus 2.66%. This is basically expressing the error as a fraction of true value, because the denominator here is AT or true value. Now this error can also be expressed as a percentage of full scale deflection. We know that the range of the instrument is 0 to 2.5 volt. Therefore, full scale deflection FSD is equal to 2.5 volts. So expressing error as a fraction of full scale reflection, ER, let's say FSD is equal to dou A by full scale deflection, which is 2.5 volts, is equal to minus 0.04 by 2.5 volts, which is minus 0.016, and expressing this as a percentage ER FSD is equal to minus 1.6%. Okay, the next parameter we need to learn is uncertainty. Uncertainty is defined as a parameter associated with the result of measurement that characterizes the dispersion of values that could reasonably be attributed to the thing being measured. Okay, that's a cool formal definition, but how is uncertainty any different from accuracy? Remember the definition of accuracy we discussed in the last video. Accuracy is the nearness of indicated value to the true value. But in practice, we will never know the true value of any quantity. Even with the finest measurement instruments, perfect values cannot be realized. It is simply impossible to define or make perfect measurements. Neither nature nor the laws of physics allow it. But in the case of uncertainty, such a problem does not arise. This is because it does not attempt to define or rely on one unique true value. Uncertainty is typically expressed as a range of values in which the value is estimated to lie. So, does the difference between accuracy and uncertainty really matter? I would say no, because in many situations, the difference really doesn't matter at all. Also, it is much easier to say that the instrument is accurate to rather than the instrument is uncertain by. And an accurate device sounds more impressive than an uncertain device, right? So, in the modern world, these terms are often used interchangeably. Next, we have repeatability. It reflects the closeness of agreement of a group of output signals obtained by the same observer for the same input quantity using the same methods and apparatus under the same operating environment but over a short time span. I don't think this requires any more explanation. To put it simply, repeatability is the characteristic of precision instrument, and the term is generally applied to quote the standards of performance of measuring instruments. Okay, now we have reproducibility. It is the closeness with which the same value of the input quantity is measured at different times and under different conditions of usage of the instrument and by different instruments. Therefore, the output signals and indications are checked for consistency over prolonged periods and at different locations to determine the reproducibility of instruments. Perfect reproducibility ensures interchangeability of instruments. That is, if the instrument at one site fails or breaks down, it can be replaced with another instrument of the same kind. Okay, so that was reproducibility. Now the next parameter we need to learn is stability. Stability defines the ability of measuring system to maintain its standard of performance over prolonged periods of time. An advantage of instrument with high stability is that it need not be calibrated frequently. The next term we need to learn is zero stability. Zero stability defines the ability of an instrument to restore to zero reading after the input quantity has been brought to zero while the other conditions remain the same. For example, while measuring current, you might have seen that some ammeter readings does not come back to zero even though you have brought the current back to zero. So there is a slight offset. That is, the indicator does not come back to zero even though the current value is brought back to zero. So this is because the instrument has low zero stability. Okay, so we have covered zero stability also. The next term we need to learn is resolution. Resolution is the smallest increment of the input quantity that gives some small but definite numerical change in the output. That is, if the input is slowly increased from some arbitrary value, it will be found that the output does not change at all until a certain increment is exceeded. This increment is known as resolution. As an example, if you have a clinical thermometer, the smallest temperature it can measure is 0.1 degree Celsius. It cannot detect any change of temperature below 0.1 degree Celsius. That is, it cannot measure temperatures like 0.01 degrees Celsius or 0.001 degrees Celsius. So the resolution of thermometer is 0.1 degrees Celsius. Let us now see a question related to resolution. A moving coil voltmeter has a uniform scale with 100 divisions. The full scale reading is 200 volt and 1/10 of the scale division can be estimated with a fair degree of certainty. Determine the resolution of the instrument in volts. Okay, so the instrument has 100 divisions and the scale is uniform. Also the full scale reading is 200 volt. So one scale division corresponds to 200 volt by 100 because 100 divisions are there, which is 2 volts. And it is said that 1/10 of a scale division can be estimated with a fair degree of certainty. What it means is that we can determine a change of voltage corresponding to 1/10 of a scale division, that is 1/10 of 2 volt. So the smallest change in voltage we can measure is, that is, smallest change in voltage that can be dictated using this voltmeter is 2 volt by 10, which is, that is 1/10 of 2 volt, which is 0.2 volt, and this is the resolution of the instrument. Okay, going to the next static characteristic, we have sensitivity. Sensitivity is defined as the ratio of change in output signal to a change in the input quantity. When the calibration curve is linear, as in this figure, the sensitivity of the instrument can be defined as the slope of the calibration curve. For this case, the sensitivity is constant over the entire range of instrument because this is a straight line. However, if the curve is not linear, then the incremental sensitivity is different for different values of input quantity. Okay. In general, the static sensitivity at a operating point is defined as static sensitivity is equal to infinitesimal change in output by infinitesimal change in input. That is delta Q0 by delta Qi. The sensitivity of an instrument should be high enough to develop a readable or dictatable change in output signal for the smallest change in input quantity. Also, sometimes manufacturers define the sensitivity of their instrument in terms of inverse sensitivity. It is defined as the inverse of static sensitivity. That is, inverse sensitivity is equal to 1 by static sensitivity, or delta Qi by delta Q0. Now this inverse sensitivity is also called deflection factor. Okay, let us now see an example related to the topic. A Wheatstone bridge requires a change of 7 ohm in the unknown arm of the bridge to produce a change in deflection of 3 mm of the galvanometer. Determine the sensitivity. Also determine the deflection factor. So here the change in input quantity is 7 ohm and the change in output quantity is 3 mm. So sensitivity is equal to delta Q0 by delta Qi, which will be 3 mm by 7 ohm, which is 0.429 mm per ohm. And we are also asked to find the deflection factor, or which is inverse sensitivity. Therefore, deflection factor is equal to 1 by sensitivity, which is 1 by 0.429 millimeter per ohm, which is 2.33 ohm per millimeter. Now, the sensitivity of an instrument is affected by environmental conditions and disturbances. Such environmental changes cause a drift in the instrument characteristics. Drift can be defined as a slow variation of the output signal of a transducer or a measuring system which is not due to any change in the input quantity. The drift is usually noticeable as zero drift and sensitivity drift. Zero drift describes the effect where the zero reading of an instrument is modified by a change in ambient conditions. This causes a constant error that exists over the full range of the measurement of instrument. A weighing machine is an example of an instrument prone to zero drift. It is quite usual to find that the reading of the instrument is perhaps 100 gram with nothing on the scale. If something of non-weight, say 10 kg, were to be kept on the scale, the reading would be 10 kg and 100 grams. And if something of non-weight, say 20 kg, were to be kept on the scale, the reading would be 20 kg and 100 grams. So you can see that this 100 gram error is present throughout the scale of the instrument. Zero drift is normally removed by calibration. This graph here shows a typical change in output characteristics due to zero drift. This difference between the characteristics at zero is the zero drift. And one more thing, zero drift is also called bias. Okay. Next we have sensitivity drift. Sensitivity drift defines the amount by which an instrument's sensitivity of measurement varies as ambient conditions change. It is quantified by sensitivity drift coefficients that define how much drift is there for a unit change in each environmental parameter that the instrument characteristics are sensitive to. You will get a better idea of what I meant by this when we see an example. Here is a figure that shows the effect of sensitivity drift on the output characteristic of an instrument. The difference between the slopes of two characteristics is the sensitivity drift. That is, the slope of this nominal characteristic, that is, this characteristic is A, and the slope of this characteristic is B, then sensitivity drift is B minus A. Also, another name for sensitivity drift is scale factor drift. Scale factor drift. Now, if an instrument suffers both zero drift and sensitivity drift at the same time, then the typical modification of the output characteristic is like this. Now let us see some examples on sensitivity drift and zero drift. The following table shows the output measurements of voltmeter under two sets of conditions. A, used in an environment kept at 20 degrees Celsius, which is the temperature that it was calibrated at. B, used in an environment at a temperature of 50 degrees Celsius. So here are the readings at 20 degrees Celsius and here are the readings at 50 degrees Celsius. We are asked to determine the zero drift when it is used in 50 degrees Celsius environment, assuming that the measurement values when it was used in 20 degrees Celsius environment are correct. Also, calculate the zero drift coefficient. Okay, let us first determine the difference between the pairs of output readings. In the first case, the difference is 10.5 minus 10.2, which is 0.3 degrees Celsius. In the second case, it is 20.6 minus 20.3, which is also 0.3 degrees Celsius. Similarly, in this case also 0.3 degrees Celsius and here also 0.3 degrees Celsius. Okay, you can see that 0.3 degrees Celsius is a constant difference between the output pairs. So the zero drift at the temperature of 50 degrees Celsius is zero drift at 50 degrees Celsius temperature is 0.3 volts. Now we are also asked to find zero drift coefficient. So zero drift coefficient. Zero drift coefficient is the ratio of magnitude of drift to the magnitude of temperature change causing the drift. That is, magnitude of drift divided by magnitude of temperature change causing the drift. That is, here the magnitude of drift is 0.3 volt and the temperature change is 50 degrees Celsius minus 20 degrees Celsius. 50 degrees Celsius minus 20 degrees Celsius, which is 0.3 by 30 degrees Celsius or 0.01 volt per degree Celsius. So this is the zero drift coefficient. Let us see one more question related to the topic. A spring balance is calibrated in an environment at a temperature of 20 degrees Celsius and has the following deflection load characteristic. At 0 kg we have a deflection of 0 mm, and at 1 we have 20, 240, 360 and so on. Also given that it is then used in an environment at a temperature of 30 degrees Celsius and the following deflection load characteristic is measured. When the load is 0 kg, the deflection is 5 mm. When the load is 1 kg, the deflection is 27 mm, and so on. So we are asked to determine the zero drift and sensitivity drift per degree Celsius change in an ambient temperature. The first thing we need to do is plot these data into a graph. So let us take x-axis as load and y-axis as deflection. Now when the load was 0 kg, the deflection at 20 degrees Celsius was 0, while the deflection at 30 degrees Celsius was 5 mm. Similarly, when the load was 1 kg, the deflection at 20 degrees Celsius was 20 mm, while the deflection at 30 degrees Celsius was 27 mm. Similarly, for 2 kg we had 40 and 49, and for 3 kg we have 60 and I believe it was 71. Yeah, so 71. Now plotting these as lines. Here is our graph. At 0 readings we have 5 and 0, and at full scale reading we had, or at a 3 kg load we have 71 and 60. Now let me copy and paste this in our blackboard. So this axis is deflection and this axis is load, and this is the characteristic at 20 degrees Celsius and this is the characteristic at 30 degrees Celsius. Now as we have already discussed, the magnitude of zero drift is this difference, that is 5 mm. So the zero drift is 5 mm. And to find the zero drift coefficient, we have zero drift by change in temperature, which is 5 mm by change in temperature was 30 degrees Celsius minus 20 degrees Celsius, which is 0.5 mm per degree Celsius. Now to find sensitivity drift, let us calculate the slope of these two lines. The slope of this line is S1 equal to 60 minus 0 by 3 minus 0, which is 20 mm per kilogram, and the slope of this line is S2 equal to 71 minus 5 by 3 minus 0, which is 22 mm per kilogram. Also we know that sensitivity drift is equal to slope of characteristic at new temperature minus slope of characteristic at nominal temperature, or the temperature at which the scale was calibrated. Okay, and here the slope at new temperature is 22 mm per kilogram, and the slope at nominal temperature is 20 mm per kilogram, and this is 2 mm per kilogram. So that is the sensitivity drift. Now we need to calculate sensitivity drift coefficient. So sensitivity drift coefficient is equal to 2 mm per kilogram by change in temperature, that is 30 degrees Celsius minus 20 degrees Celsius, which is 10 degrees Celsius, and is 0.2 mm per kilogram per degree Celsius. Okay, so we have covered drift also. Next we have responsiveness. Responsiveness denotes the change in quantity under measurement, which results in an actuating effort required to cause motion of the indicating part of the instrument. Now please don't confuse it with resolution. The definition of both these terms looks similar but not the same. In the case of resolution, it was the smallest input that bring about a definite numerical change in the output, that is, the smallest measurable input change. However, in the case of responsiveness, we don't need a numerical change in the output. It is the smallest input that can cause a movement of the indicating part of the instrument. This movement need not be big enough to be noticed, let alone get a reading. Now let us take a look at the concept of linearity. Linearity defines the proportionality between input quantity and output signal. In simplest words, a system possesses linear behavior if the relationship between its input and output is a straight line. However, most of the time, it is not necessary that the measurement system has a linear characteristics. It may be non-linear, like this graph or like this. So, we try to fit a straight line that approximates the characteristics, like this or like this. As you can see, the original characteristic deviate from the best fit line we drew. So, in the measurement sense, linearity can be defined as the maximum deviation of output reading from the good fit straight line. This deviation from straight line may be expressed by a term percentage linearity. Percentage linearity can be defined as maximum deviation by full scale deviation into 100. This percentage linearity can be expressed in terms of maximum deviation of input value or maximum deviation of output value. In either case, the percentage linearity is the same. For example, in this graph, the maximum deviation occurs almost around here, right? So, this is the maximum deviation in input, and let us write it as x1. And this is the maximum deviation in output from the good fit straight line, and let this be y1. Also, the full scale value of input is, let's say, x max, and the full scale value of output is, let's say, y max. Then percentage linearity can be expressed as x1 by x max into 100 or y1 by y max into 100. And note that both these values are equal. Now let's see an example so that the concept becomes more clear. A 10,000 ohm variable resistance has a linearity of 0.1% and the movement of contact arm is 320 degree. So we have a variable resistance like this, and at this end we have 0 ohms and the resistance increase along the circumference, and at this end we have 10,000 ohms. Similarly, this position corresponds to 0 degree and this position corresponds to 320 degree. So in usual case, both this degree and resistance should increase linearly. That is, this is degree and this is resistance, then it should increase linearly. But it is said that there is certain linearity present in the system, that is, there is certain deviation from the straight line. So the original graph may be somewhat like this, maybe, I'm not sure. Okay, so we are supposed to find the position of maximum deviation of original curve from the straight line. So let us write down the given variables. Full scale value of resistance is, full scale value of resistance is 10,000 ohm, and full scale value of contact arm or rotation of contact arm is 320 degree. Now we are asked to determine the maximum position deviation in degrees. So using this relation we have maximum position deviation equal to percentage linearity into full scale deflection or deviation by 100, which is percentage linearity is 0.1%. So 0.1 into full scale deviation in degrees, that is 320 degree by 100, which is 0.32 degree. So that is the maximum position deviation in degrees. We are also required to find the resistance deviation in ohm. Therefore, maximum resistance deviation is equal to, again, percentage linearity, which is 0.1 into full scale deviation in resistance, which is 10,000 ohm by 100, which will be 10 ohm. Now the second part of the question is, if this instrument is used as a potentiometer with a linear scale of 0 to 1.6 volt, determine the maximum voltage error. So it is said that there is a linear relationship between the position in degrees theta and the voltage range 0 to 1.6 volt. So we get a linear scale like this, and these values are 320 degree corresponds to 1.6 volt, and here we have 0, 0. So we can see that the voltage and the degrees are related by V is equal to 1.6 volt by 320 degree into degrees. And we know that the maximum deviation in degrees was 0.32 degree. So the maximum voltage error occurs at 0.32 degree. Let us find the voltage corresponding to 0.32 degree. Therefore, 1.6 by 320 degree into 0.32, which is 1.6 into 10 raised to minus 3 volts. So the maximum voltage error is 1.6 millivolt. The next parameter we need to learn is threshold. Threshold is defined as the minimum input quantity that is necessary to cause a dictatable change in the output signal from the zero indication. For example, if we see the input-output characteristics of a diode, we can see that the output is 0 until the input reaches a certain non-zero value. This non-zero value is called threshold. Lastly, we have deadband. Deadband or deadzone is the largest value of input variable for which the instrument output stays the same. For example, we often find that the ammeters tend to stick, that is, the mechanical arrangement don't move due to inertia or static friction. So what happens is, till you send a certain amount of current, the torque is not enough to overcome this static friction. So the indicator needle doesn't move. Another example of deadzone is backlash in gears. Here, if this is the driving gear, and this is the driven gear, and this gear rotates in this direction, then you can see that there is a small gap between the gears initially. So if we rotate the driving gear, the motion won't be transferred to the driven gear until the gap closes. If we consider the degree of rotation of the driving gear as input, that is, this is gear 1 and this is gear 2, and the degree of rotation of driven gear as output, we can see that even though there is input, the output remains 0 for some time. After that, there is a linear relation. Similarly, if we rotate the driving gear in opposite direction, the gear 2 remains in the same position for some time due to that gap, and after that there is a linear relationship. So this is the direction of motion. Similarly, if you rotate in the opposite direction, then this will be the direction of motion. So the entire characteristic look like this, and this is the deadzone. Okay. One more parameter that is usually associated with static characteristics is hysteresis. Hysteresis is a phenomenon where if we gradually increase the inputs, the characteristics follow one path, and if we gradually decrease the input, the characteristics follow another path. This completes our discussion on static characteristics. This was a lengthy video and we had studied a lot of static parameters. So let us have a brief summary of what all we studied in this lecture. First, we studied about static error, which is defined as measured value minus true value. We also saw relative static error, which was the ratio of static error to true value. Then we learned about uncertainty, which is expressed as the range of values in which the value is estimated to lie. After that, we learned repeatability and reproducibility. Then we discussed about stability, zero stability, and resolution, followed by sensitivity, drift, linearity, threshold, and deadzone. So, in the last two lectures, we have covered everything there is to learn on static characteristics. If you found the lecture useful, please like the video and also support us by subscribing to the channel. Also, if you have any doubts, leave them in the comments below. I'll try to answer them with the best of my knowledge, or some other viewer can also help you. In the next video, we will start our discussions on dynamic characteristics. Thanks for watching and have a nice day.